Yeah, thank you very much, and thanks for inviting me to this nice program. I'm very happy to be here. So the name of this workshop was Recent Advances in Algebraic Ktheory. So I was not so sure what precisely recent means, and I give this course of 3 lectures, and it's mainly intended for the somehow non-experts. So I apologize to all the experts that are here in the audience, which are quite a lot, I see. So it will be for them somehow. Probably at least the first lecture will be just recollections of known stuff. But anyway. So this is all what I do today is all quite classical. So I will introduce this notion of localizing invariants, and the goal is somehow to explain or recall how you prove the fundamental descent theorems, like that like any localizing invariant satisfies Nisnevich descent or Zariski descent. So that's the plan for today. And then tomorrow I will explain maybe how you use this to prove excision type statements in algebraic K-theory. And then at the last talk I want to use it to, I saw that there's also something on CDH, sheafified things. So I thought I also say something about K-theory and CDH topology. And so then I will try to explain how you prove some pro-CDH, so K-theory does not satisfy descent for the CDH topology, but you can somehow, there's a variant which is called pro-CDH descent, and I will try to explain this so that at least that there's something new for non-Noetherian like QC, QS schemes. Okay, so but let's start with this classical things and is this readable? Is it big enough? Okay, yeah, okay. So let me also now start first with an introduction, very even more classical. So to K-theory. So if you have any ring, then Quillen associates to it the K-theory of A, which is really defined in terms. So Quillen defines it in terms of the category of finitely generated projective modules. So this is an exact category in the sense of Quillen. So it means you have some notion of exact sequences and so on that satisfies some axioms. And okay, so that's some definition. And maybe in modern terms you could say this is defined as you take this category, finitely generated projective A modules. This has a direct sum operation, so that's symmetric monoidal with respect to direct sum. And then you take So you take the underlying, how do I write this, groupoid, so throw away all the non-isomorphisms, and then you can, so that's a groupoid, you can view it as a space, or in fact, that's somehow an E-infinity space, which is not group-like, but then you can group complete it, and okay, let me write it like this. So this is now this is an E-infinity group. Or in other words, that's also the same. You can view it as a connective spectrum. Okay. Yeah. So that's also called connective K-theory. This is an important point that will come up later. So there are no negative K groups by definition in this thing. So the K groups are the homotopy groups of this. Okay, and now you want to start computing it, so you need some type of descent statements. For example, if you have a Zariski covering, an affine Zariski covering of your ring, you maybe want to deduce something about the K-theory of A in terms of these covering things. And this is not so easy to prove with this definition. So the problem is, so Quillen has some theorems, but so Quillen theorems, for these exact categories mainly work for abelian categories. So somehow this implies that it's hard to prove descent statements with this definition of K-theory. Okay. Yeah, because this is not an abelian category in general. Okay, and then someone was I think it goes mainly back to Thomason, but maybe influenced also by Grothendieck, that the point is you should, so Thomason proposed that you should replace this category of finitely generated projective modules by something called the category of perfect complexes, so perf of A. So let me say what this is, maybe here again. So these are just finite complexes of finitely generated projectives. And so nowadays you can view it as an infinity category. So that's a small stable infinity category. And in fact it's also the same as the compact objects. In the infinity derived category of this ring A. Okay, and then somehow yeah, what you might then the main point is that you have a so-called I think it's called Waldhausen. I wrote down localization, but I think it's called Waldhausen's vibration theorem. So Waldhausen somehow further developed K-theory, or has an alternative definition of K-theory for so-called Waldhausen categories, and he has a so-called vibration theorem, which gives you sometimes somehow fiber sequences of K-theory spectra. For if you have a sequence of categories, and then somehow you have purely categorical arguments that your category satisfies something, and this will produce fiber sequences of K-theory spectra. Okay, and these are somehow satisfied quite often. So okay, so this was a very short introduction, and now I come to a bit more details. So the first paragraph is on localizing invariants. Okay, so as we saw here, somehow the important thing is the K-theory really yeah. So maybe the point here is that you can define the K-theory of A also in terms of this category, okay, or more generally in terms of any for any small stable infinity category you can define a K-theory spectrum, and then somehow I want to formulate the analog of this Waldhausen vibration theorem, and somehow the functors which satisfy this are called localizing invariants. So now let me make this a bit more precise. So I need some technical preliminaries, some on Verdier quotients. First of all, okay, so the setting is we have a small stable infinity category C. And then we look at some subcategory D. It's also a stable subcategory. And then we can define the Verdier quotient. So okay, now I have to now how do I do this? So this should go completely up. I think I continue on this one here.
Maybe I ask you a basic question. What do you mean by connective in the commutative groups?
Can you say again?
What do you mean by connective K-theory?
Yeah. So this is a connective spectrum, and this thing is called connective K-theory because there's also a non-connective K-theory, and somehow localizing in the sense that I will define is so connective K-theory is not a localizing invariant, but you need to introduce negative K groups.
Okay. So connective means starting from K0 without the negative, so it doesn't mean the space is connected because it has pi 0.
So connective means there is some pi 0, which could be non-trivial, and then you have also...
Okay, so this is the terminology in topology, that connective is not connected. Okay.
It's not connected. Yes, so this one has I mean, so pi 0 is just the ordinary K0 group completion of the isomorphism class.
It's just vanishing of negative.
So this, by definition, this vanishes in negative degrees. Yes. Okay. So I wanted to. So we have the subcategory, and then we define the Verdier quotient. And so there's several ways. For example, you could define it as the co-fiber of the inclusion functor of the inclusion map from D to C inside the category of small stable infinity categories. But there's an explicit description, so you can write this. So that's some localization of this category where you invert formally all the maps which are somehow isomorphisms mod D. So you invert all maps from C to C prime, let's say F, whose co-fiber of F lies in this category D. Okay, so this just some formal process to define this category, this Verdier quotient, and so in other words, so this has some universal property. So this means that functors out of this category C mod D. Okay, let me maybe also introduce. So there's a canonical map from C to this localization, and functors out of this Verdier quotient to any other infinity category. So E doesn't have to be stable, right? So this is any infinity category. This is the same as functors from C to E with some decoration W here. So this is a full subcategory of all functors from C to E. And this here means that it sends, so that's the subcategory of functors that sending such F in W to equivalences in E. Okay, so that's a definition. And then first of all, I mean, if you define it like this, it's not obvious that this category will be stable again, but this is something one can prove. So facts. So this C mod D is stable. And you also have a similar, here's, so the important point is of course this, so the this functor is induced by somehow precomposing with this functor from C to C mod D, and this induces an equivalence like this, okay? So this is stable, and it also has a universal property for maps for functors into stable categories. Namely, do I even need this? Yeah, maybe. Why not? So functors, exact functors out of C mod D into any E. So here now E is also stable. This will also be equivalent to functors from C to E, which send D to 0. So let me indicate it like this: D goes to 0. Okay. Yeah. So that's the definition of the Verdier quotient. And another fact is that somehow you have a quite explicit formula how to compute the mapping spaces inside this category. So if, let's say, X and Y are in C and their images X bar and Y bar in the Verdier quotient, then so somehow there's some how it's called calculus of fractions formula for the mapping spaces in the Verdier quotient. So let me maybe fit it here. The mapping space in the quotient from X bar to Y bar, this is given by some filtered colimit. Namely, you look at maps in the category in C from X to, and then, okay, how do I write this? Yeah, so you look at any Z in the slice category, D over Y. So you should think of these somehow triangles like this. You have a Z which is in the subcategory D that you are modding out, and then you can look at a map to the cofiber of this. Let's call it G. So this map here from Y, so because this is in D, this map here, this will be a typical element in the set W that we invert formally. And you should look at, think of these triangles. So that's here and then the cofiber of this map from Z to Y. Okay. Yeah, by the way, I just, so I have a list of references. So I have a PDF file on my computer. I don't know what to do with it, but so this is of course all very classical. Somehow, I don't know. I mean, you can look in Niemann's book on triangulated categories and so on, for example, and somehow in this infinity categorical language you find an account, for example, in the paper by Nikolaus and Scholze on topological cyclic homology. Yeah, so maybe I can make this list of references available somewhere. This would be useful.
It can be put on the website.
Ah, okay, good. Okay, so this is one point. Somehow these Verdier quotients, and
so in particular, D over Y is filtered.
Yes,
in the infinity sense of it.
Because D. Yeah, thanks. Yeah, because D is stable, so. So this category here is a filtered category. You can just, if you have any finite diagram, you can just take the co-limit and this somehow you find the cone. So you see that this, yeah. Okay, so that are Verdier quotients, and then there's an important point somehow that you can, which is quite useful. Is so these are the small categories, but it's often useful to pass to large categories via the incompletion. So let me also say something about the incompletion. Maybe, yeah, okay, let me start here. Incompletion. So C is...
Maybe I missed some point. So your small map means what?
What?
So this is this map.
Which one?
No, I mean MAP.
Thanks. Maybe you can also... Okay, sorry. Maybe you can take capital.
I'm not getting you.
Is it, yeah, so that's the mapping space.
Okay, so it is also true for spectra invariants.
It's also true for the mapping spectra, yes. So you can also write little m. But I think I want to use this notation for mapping spaces, and for mapping spectra, I think I will use the notation HOM. So, thanks. Okay, so we have so C is again small, stable. Then we often pass to the incompletion, and the point is somehow that, so this is now a presentable category, and then you have adjoint functor theorems and so on that you can use, which you don't have for small categories. And how is it defined? So you can define it, for example, as a full subcategory of presheaves. Okay, so that's a curly S and stands for spaces, or anima if you like. And how do you define this? So this is just somehow the full subcategory of this one spanned by filtered co-limits of representables. And then from this definition you see, so you have the Yoneda embedding from C into presheaves, and this factors over this incompletion. Okay. What did I want to say here? Yeah. Okay, so now you can ask yourself, can you somehow recover C from the incompletion? And that's not quite true, but almost. So first of all, you see that C is always contained in the compact objects inside the incompletion. So this here, omega means compact objects. So yeah, this you just check by checking the formula for mapping spaces in the functor category here. Somehow the object of C, I mean, in this category somehow mapping out of them commutes with arbitrary co-limits, and in this category it still commute with filtered co-limits. So these are compact, but in general this will not be an equivalence. Okay, and it turns out that. Okay, so this one here is the so-called idempotent or Karubi completion of C. So in other words, this category here is closed under retracts, and every object of C here is a retract of some object of in the incompletion. Okay, so that's actually quite easy to check. So if you have any what did I say? Any sorry, conversely, any object in the incompletion is a retract of some object of C. So if you have any x in the incompletion, then you just write this as a filtered colimit of objects of C, which is possible by definition. So x is equivalent to some filtered colimit of Ci's. So this is some filter diagram, and this is compact. Take a compact object, but now you have a compact object mapping into some filtered colimit. So this means that this map already factors over one of the Ci's. So you get a factorization like this. And so this shows that x is a retract of the Ci. Okay. Yeah. So this is the connection to the incompletion, and so the point here is, I think I didn't write this before. So sorry. So int of these. This is now a presentable, stable, and compactly generated infinity category. So this presentable, stable, compactly generated infinity categories. And some of the, as we saw, the passage from small stable infinity categories to the incompletion here, this is almost an equivalence of categories. Not quite, because you only get the idempotent complete infinity categories here. And these are some of the main players for localizing invariants. So let me define this. Yeah.
I'm confused. So do you suggest that these are compact objects in this thing, because your notation you write an omega there. I mean PRL is a category. Is it?
You mean this omega?
Yeah.
No, these are not the compact objects inside this category. But
what is the superscript? PR, ST.
So this ST means stable. PRL means I mean this means you consider functors which are left adjoints or preserve filtered colimits, and omega means these are compactly generated, and you restrict to functors those functors which also preserve compact objects, or in other words that the right adjoint preserves filtered colimits. Okay, so let me define now. So we give a name to this category of idempotent complete stable infinity categories, and this is cut perf, also part one of the definition. So that's the infinity category of idempotent or Karubi complete small stable infinity categories. And just as a remark here, but the incompletion gives an equivalence of cut perf infinity to this category of compactly generated stable infinity categories. And somehow maybe also let me also point here to Dustin's course. Maybe I will do this again later. So the point is somehow this means that K-theory, so in K-theory we can plug in some of these perfect categories, but the statute that you could also plug in these large categories by first passing to compact objects. And some of the point of Efimov K-theory that Dustin will talk about is precisely to extend this from these large categories to a bigger class called the dualizable stable infinity categories. Okay, so this is this was this. Yeah. Then we need the notion of somehow a notion of short exact sequences, and this as follows. So let's say D to C and then to E. Let's call this I and this P. So that's the sequence of functors in Cut-Perf. This is called a Karoubi sequence. So you might also, sometimes it's also called exact sequence or some other kind of word. I'm insisting on this Karoubi here, and I took this, I think, from this 9-author project on Hermitian K-theory. Because it makes a difference. So okay, let me define it and then I explain this. So first of all, we want that the composite of these functors, there was an infinity, is 0. So P composed with I is 0, and you can check this is really a condition. That's not an additional datum. So some of the space of null homotopies of this composite is contractible, or it's empty. That's the first condition. Okay. So now this composite is 0. So this means you get a. Let me also say, so I is fully faithful. So this, you can really view D as a subcategory of C. And now you get an induced map from the Verdier quotient of C mod D to this E here. And so the induced functor from C mod D to E. And this, in general, if you take the Verdier quotient, even if these here were idempotent complete, this does not imply that the Verdier quotient is idempotent complete. Okay. So we want that this map here is an idempotent completion. Okay, now I've already used all these boards. So let me switch to the next one. And now I can define this notion of a localizing invariant. And so to be precise, one should also call it maybe Karoubi localizing invariant. But in my course, I will only look at these Karoubi localizing invariants, so I will just say localizing invariant. And so this is a functor from this category of Karoubi complete small stable infinity categories to some stable infinity category, or usually to spectra, which sends these Karoubi sequences to fiber sequences. So sending Karoubi sequences to fiber sequences. Okay, so this is just a definition, and
so in Karoubi sequence, the composition being 0, you don't have to specify the homotopy somehow unique up to 0 doesn't have, as far as I understand. As far as I understand, in the fiber sequence, you have to specify the homotopy for the composition, and in the Karoubi sequence, it does a condition object by object. But you get something isomorphic to a 0 object, isn't it?
I mean, the point is that you can look at this composite, and this could be null homotopic or not. If it is null, I mean, somehow you can define the space of all null homotopies, and this is contractible, or it's empty. So it's really a condition. Yeah.
But in the fiber sequence,
in general, for if you have an arbitrary infinity category, of course, if you have a fiber sequence, then there could be different. Yeah. Okay.
But this notion is a priori also slightly different from fiber sequence, right? I mean, it is also co-fiber score, whatever. I mean.
So this Karoubi sequence is also the same as being a fiber, simultaneously a fiber and a co-fiber sequence in this category. That's also true. Yeah. Okay.
Why do you require idempotent to be idempotent complete?
It's an idempotent completion. So the point is this one is idempotent complete by assumption, but the Verdier quotient in general not. And the condition is this is an or in other words, this map here, this function induces an equivalence on idempotent completions. Okay, more questions. Okay, okay. Now there's some of the fundamental theorem that goes back to work of many people, is that K-theory is a localizing invariant in that sense. And here I really have to be careful and talk about non-connective K-theory. So let me maybe list a couple of names here. So somehow you need this Waldhausen vibration theorem. And then I think the first one who really used this, including the negative K groups, was Thomason in the work with, I mean, Thomason-Troubaud on the K-theory of schemes. And but this is still in the special setting somehow of schemes. And then Schlitting defined negative K groups also for certain exact categories, which you use here. And and then in this infinity categorical language, it was first proven by Blumberg, Gepner, and Tabuada. But somehow, if I understand correctly, at least, or if I remember correctly, somehow they used this previous work of Waldhausen and Schlitting and so on. And now there's also a modern, somehow independent approach by Fabian Hebestreit, Andrea Lachmann, and Wolfgang Steimle. So let me put all these names here. So K-theory. And now it's important that I say this non-connective K-theory. Is localizing in this sense. So I mean, just once is Karoubi localizing.
So is the last thing you mentioned like written somewhere?
Yes, you will find. I mean, this is just a somehow. I mean, the nice thing. This is purely infinity categorical, and doesn't use the old language. And that's on the archive. If you Google for these three names, you will find it. Or if you wait for my list of references, it's also written there. Okay.
Are you going to define the non-connective K-theory?
No, let's take this as a black box that it exists. Okay. I mean, you can also, I don't know, okay. You can also define it as the universal invariant somehow which satisfies this property. That's a possible definition. Or, I mean, for rings, somehow you can define the negative K groups by somehow forcing the fundamental theorem, or yeah.
There was also a definition for associative rings of negative K groups.
Yes.
And I think they proved that all the, like Schlichting, I mean, they know that all the negative K groups, all the definitions are equivalent, I think, but I'm not an expert in this. So I remember there was a definition for general rings,
yes,
using some suspension. Then for
yes, this is also possible, yes.
Commutative, there are like in Thomason-Troubaud.
Yeah. But I mean, the negative K groups for arbitrary rings were already defined by Bass, I think, in the book.
And all those definitions are compatible.
Yes, I think so. Yeah. Okay. I mean, so somehow so roughly, what is the idea of Schlichting, or for if you have such a small stable infinity category, is you embed it in a larger infinity category, which has arbitrary direct sums. And so whose K-theory vanishes, and then you take the co-fiber of this, and this somehow gives you a delooping of this category. Okay, and of course then you have to do this somehow infinitely often to get all the negatives. So this would produce a K-1, and then you do this infinitely often. Okay. But somehow I want to, just want to take this as a black box. There's some invariant called K-theory, which is Karoubi localizing, and then I want to explain somehow how you use this to actually prove something about the K-theory of schemes. Okay, and also maybe another comment is there are some more localizing invariants, but not so many, I think. I mean, basically, I only know one, which is THH. Some of this, I think KT and THH are some of the basic localizing invariants that we know, and then of course everything you can build out of these is also localizing, like TC and TP and whatever. And you can also restrict your input. You allowed some of the domain of definition to like Z linear categories or something, or Q linear categories, and they can also do something like periodic cyclic homology. I mean, classical periodic cyclic homology, and cyclic homology relative to some base Q. And so on. These are also localizing then on this subcategory of for example, Q linear stable infinity categories. But I don't know. I mean, is there any other localizing invariant that we know? I mean, how do you define it for arbitrary?
I mean, Blanc defined it.
Yeah, but isn't it also built out of something here? I mean, K-theory and so on by some.
Maybe it's just worth saying that in Waldhausen's lectures, probably. I mean. So some more examples will come. I mean, for example, one thing you could take Holmes in non-connected motives out of.
Yeah. Okay. Yeah. Okay. Good. Okay. So now I've defined what this is. Now I want to explain how you prove something with it. And there's one tool that you need. So we know that for every such Karoubi sequence, we get a fiber sequence of K-theory spectra. This is of course nice, but first of all, we need some of these Karoubi sequences. Okay, so the question is how to get them. And that's the classical so-called Thomason-Niemann localization theorem. Localization. So some of the question here is how to produce these Karoubi sequences. Okay, so somehow you're given put it differently, somehow you're given some candidate sequence like this, and you want to check if it is a Karoubi sequence. And this, if you do it on this level of small categories, that's maybe not so easy. But the point is, once you pass to incompletions, you have presentable infinity categories, and then you have adjoint functor theorems and so on. And then it's often easy to check if somehow the result is the version of Karoubi sequence for presentable infinity categories. And so this is somehow what this theorem gives us. So the setting is as before. C is let's say cut path, and D is a stable subcategory. And so what this theorem says is what is it? Oh yeah, okay. So we can look at the. So let me introduce a bit more notation. Let's call this canonical functor from C to the Verdier quotient P from C to C mod D. And then the theorem is that if we pass to incompletions here, so int of C to int of C mod D, so that's the incompletion of this functor P, and this will also be called L, because it's a left adjoint. So this is a so-called Bausfield localization. So this means this functor here has a fully faithful right adjoint. So this has fully faithful right adjoint. And then you can look at the kernel of this functor, so there's the subcategory of all objects that map to something equivalent to 0 here. And this is precisely given by the incompletion of D. So the kernel of L is precise. And the right adjoint has a name R. And the kernel of this, the left adjoint, the localization functor, is precisely the incompletion of D. Okay. So, by the way, so how much time do I have until?
12:35.
12:35. Okay, it's not so bad, I think. Yeah. So in particular, this means this implies that the incompletion of the Verdier quotient is also the Verdier quotient of the incompletions here, int of C mod int of D. Okay. So let's indicate how you prove this. Here. This doesn't go up so far. Okay.
The condition of being Carobian shouldn't appear here because we pass to int.
Yes, this is true. I mean, this is This holds more generally for any small stable infinity category. Yeah, that's correct. But soon we want to parse back somehow, taking compact objects, and then it's important to have something idempotent closed, Karoubi closed. Okay, so first of all, why does it have a right adjoint? So L has right adjoint. I mean, this is quite easy now. So by definition, you see that this functor this functor L here, this commutes with all filtered colimits, but everything is stable here, and then the functor is also exact, so it also commutes. So then it commutes with all colimits, and then you can imply the adjoint functor theorem, and this gives you that it has a right adjoint. So this has a right adjoint by adjoint functor theorem. Okay. Right adjoint R. And it's even easy to explicitly write down what this functor R is, at least on the image of C mod D in this Verdier quotient. So on C mod D, this R is given by. So the point is, if you have this, let's say any functor C to D from between infinity, small infinity categories, and then you pass to the pre-sheaf categories, which is somehow the free colimit completion. So where you formally adjoin or freely adjoin all colimits, and then you get an induced functor on the pre-sheaf categories, and it's easy to check basically from the Yoneda lemma that the right adjoint is just given by precomposing with your given functor from in this case from C to C mod D. Okay, and the same is true here. So any, let's say call it Y bar, yeah, in C mod D. So this is sent to the mapping space. Now let me write this correctly. In C mod D of P, so you precompose with P, and then you take the Y bar here. Okay, so this is a functor. I mean, this is written here. That's a pre-sheaf on C up to spaces. But from this explicit formula that I've written down somewhere here before, you see that this is in fact. So this lies in fact in. How do I write this? Maybe like this. In fact, lies in the incompletion of C mod D inside here. As noted before, that this formula is it up there. This explicitly writes this thing as a filtered colimit of representable things. Okay. Okay. Yes. So that's the explicit formula.
We want to see in the index C, right? Not C.
It is in the incompletion of C.
Thanks. Yeah, of course. Thank you. Okay, so we have this right adjoint, and we have this explicit formula. Now we want to check maybe that it's fully faithful. And the point is here that I claim, so first of all, if you see from this formula also, if you start with something coming from C mod D, then it's given by this formula, which is what did I want to say? Which somehow is given by this explicit colimit here. And now if you apply the left adjoint again, the localization functor, this will send all these maps here to equivalences. And this will imply that if you apply the left adjoint to this right adjoint, this will give the identity. Okay, so in somehow you see it's in some sense it's fully faithful on the image of these objects in the Verdier quotient C mod D, and then now you want to extend it to all objects in the incompletion. So you need that this R also commutes with filtered colimits. Okay, and this is also completely formal. So R commutes with filtered colimits. This is again a completely formal consequence of the fact that this left adjoint here sends compact objects to compact objects. Yeah. So this is as L sends, well, let's say preserves compact objects. Yeah. So and then we see that, so from the above we see that L composed with R is the identity on somehow C mod D. First of all, this follows from this formula here. Maybe this by direct computation. And then because now both functors here commute with filtered colimits, you see that it holds in general. So this is maybe not super organized, sorry. So this implies that L composed with R is equivalent to the identity on all of int of the Verdier quotient. And this precisely says that R is fully faithful. Okay. Yeah, so that's the first part of the theorem. We have this fully faithful right adjoint, and the only thing that's left to do is the kernel of this left adjoint, and this.
Sorry, I want to just ask a question. So, yeah. So if we have a localization in small infinity categories, then we take in. Is that always true that this in the thing is a Bose field? I mean, slightly more general than this. Without stability. Just like in the C to in the C inverted double.
I think so, yes, but I'm not completely sure. Maybe someone can comment on this.
What was the question?
I mean, if you take any small infinity category and you have a localization and then pass to the incompletion, if you get a Bose field localization.
Wait, but the point for the existence of the right adjoint was that you commuted a finite.
That's true. Okay, it's not so clear, maybe, yeah. I mean, if you pass to pre-sheaf categories, then definitely yes, but if you just take the incompletion, then maybe it's not clear that you're somehow left it. I mean, this int of the localization functor preserves all colimits. That's a good point, yeah. Okay. Okay, now maybe let's also compute this kernel. So okay, let's do it over there maybe. Okay, so let's take any x in the kernel of L. Sorry. And then so this is in particular in the incompletion of C, which means you can write this x itself as a filtered colimit again of the object Ci. So that's a filtered colimit. And now we look somehow at the unit map of this adjunction. So from okay, let's do it for each Ci to right adjoint composed with left adjoint of Ci. And then again, from this explicit formula that we have, you see that this has some fiber. So this has some fiber. Let's call it di. And by construction, this from the explicit formula, you see that the phi bar di is itself in the incompletion of this category D that we took the quotient of. And now we just pass to co-limits. And then you get the co-limit of these di's here. Here you get the co-limit is x. And then again, because both functors here commute with filtered co-limits, you see that this here precisely gives you R composed with L of x, but this is 0. So you see that x is equivalent to this filtered co-limit of things which were already in the incompletion. So this is also in the incompletion. Okay, so this proves this theorem. Okay, so the point is mainly, I mean, the point was somehow to show you that this is, everything here is completely formal, this, to obtain this. Okay, so now I need some more space. Okay, but somehow the point is usually you apply this theorem in the other direction. So you are given some sequence of large categories or presentable stable categories, where it's often easy to check that that in fact you have some Bouwsfield localization sequence somehow in this sense, and then you want to pass to compact objects to get such a Karoubi sequence of small stable infinity categories. And let me formulate this, maybe this corollary. And I think in this form it's often called Thomason-Niemann localization. Localization theorem. So a sequence D to C to E, this is a Karoubi sequence. If and only if the sequence after passage to incompletion is a Bouwsfield localization sequence of int D to int C to int E is a Bouwsfield. Localization sequence in the sense that we just proved. So this functor has a fully faithful right adjoint, and the kernel of that functor is precisely this one here.
Is it the same as saying it is a Karoubi sequence?
And this is also, yes, this is also the same as saying it's a Karoubi sequence somehow in PRL-ST. But I think yes. Okay, so how do we prove this from that one? So if you have this somehow, you have this candidate sequence here, then you just compare this one with the sequence D goes to C goes to D mod C, no, C mod D. You get a comparison functor between the two by the universal property of the Verdier quotient. And then you pass to incompletions, and this theorem says that on incompletions you get an equivalence here also int. So this thing will be equivalent to int of C mod D, and then you go back by passing to compact objects. Okay, so that's the proof of this corollary, and this is the form somehow you usually apply this theorem. So you have some sequence, and it's often not so hard to prove that this one is a Bouwsfield localization because you somehow explicitly can write down what the right adjoint is here. Okay, and then you pass to compact objects. So let me just make one warning here. You could also start with a sequence of presentable infinity categories. So maybe let me write this as D hat to C hat, just to indicate that these are now large categories to E hat. Oops. So let's say this is any Bouwsfield localization sequence. Localization sequence in PRL ST. And let's also assume that we can even assume that C hat and E hat are compactly generated, so are in PRL ST omega, and also that this functor here preserves compact objects. And this does not imply that if you pass to compact objects that this sequence is a Karoubi sequence. So D hat omega to C hat omega to E hat omega is Karoubi sequence. Okay, so you have to be a bit careful if you want to apply this machinery of localizing invariants. Somehow, if you see any such a Bousfield localization, you still have to think about this D hat here. Okay, and the point is precisely that if you have the sequence, this doesn't mean it's of this form int of something. So the point is that what you need is that you always need that this kernel here is also compactly generated. And that's precisely what sometimes goes wrong. So there's a famous counterexample by someone, an example of precisely this situation by Keller, where you construct a ring together with an ideal, and you check that the map from this ring to the quotient by this ideal, on derived categories gives you like this here a Bousfield localization. So it has a fully faithful right adjoint. But you check that in this example, and that's not hard to check, the kernel has no compact objects at all. Okay. Okay, if I have some more time, I can discuss this example at some point.
Except 0, of course. What? 0 is a compact object.
Yes, thanks, except 0. 0 is the only compact object. Okay, but let's maybe see a positive example.
So can I, maybe I'm not in this area, so you define a Verdier localization before, yes. And here you say you use the word Bousfield localization, but is it the case when you work with this type of categories, it's the same or not? So any Bousfield localization will also be the Verdier localization by precisely this kernel here. Yeah. Yeah, but if you have a Verdier localization if you have what you call a presentable stable infinity category and the Verdier localization of it by a subcategory which is also in this sense, it has again presentable is nice, but then this is a Bousfield localization or not? I think yes. Okay. But yeah.
So maybe you do I think some implicit adjunction. I mean, because when you talk about Bousfield localization sequence, I just didn't get your precise definition.
Yes. So this means this functor here has a fully faithful right adjoint, and the kernel of this left adjoint here is precisely this one.
If it's not left adjoint.
So this one is a left adjoint, and the definition is there exists a fully faithful right adjoint. So this precisely as we proved in this theorem. Okay.
Assuming this sequence, the last map preserves a compact object, it doesn't ensure the kernel.
No, it does not. Yeah, but I mean that's precise in this example by Keller. This functor here is just base extension of modules along a ring map, and this preserves compact objects. Yeah. Okay. But again, I wanted to point out here that okay. Sorry, before I do this, but. The kernel, I mean, almost by definition is still dualizable, and hence you can define this Efimov K-theory of this kernel. And again, see just Dustin's course, Clausen's course. I hope these things will be explained. At least I understood so from the abstract. Okay, now let's come to some of a positive example. And that's somehow the one that gives you Zariski descent at the end. So let's say for simplicity A is any commutative ring and F is an element in A. Then we can look at the localization. So we look at the derived category of A and the derived category of the localization. So we have the space change functor given by tensoring over A with A F inverse, or just localizing. And then you see, I mean, this is very classical. This has a right adjoint which is just given by somehow forgetting the ring structure down to A, so restricting scalars. And this is fully faithful. And from this you see already that this thing here is a Bouwsfeld localization of this guy by somehow the kernel of this extension of scalars functors. And now the claim is that in this case this is in fact compactly generated. So let's say this is a Bouwsfeld localization with kernel. Okay, so the kernel is by definition D of A on F. So that's, I mean, this is just the definition of the subcategory here. So all derived modules somehow which vanish after tensoring, after inverting F. And I claim that this category here is in fact compactly generated. And I prove this by just writing down a generator. No, I did this. This was maybe stupid again.
Is this RF is the same with the derived category of A modular A?
Oh, wait, let me just put this down a second. You mean this category here? Yeah. No, it's not the same, because I mean not every object here is killed by a power of F, for example. Okay. I mean something like A mod F squared would also be in this category here, okay, if you invert F at 0, but it's not the same.
I also had a small question. Why did you remark that D is still dualizable?
So can you repeat?
What was the reason to make a remark that D hat is still dualizable?
D
hat is still dualizable.
Yeah, this is just because I wanted to advertise the mini course by Dustin Clausen. That somehow, so now we have a setting where you can make sense of the K-theory of D hat. I mean, somehow with this old machinery, you cannot talk about the K-theory of D hat because, I mean, it doesn't make sense. I mean, if you pass the compact object, you just get 0. So that's definitely not what you want to do. But so the point is when you can just define, you can pass the compact objects on C and on E, and then define some of the K-theory of this D hat to be the homotopy fiber of the K-theory of the map of K-theories from C to, I mean, compact objects of C to compact objects of E, and that this gives you a well-behaved theory. I mean, this is Efimov's K-theory. Okay. Okay, so I claim that this kernel here is compactly generated. And so the proof is quite simple. You just write down somehow one compact object in this category, which generates the whole category. So we look at K, which, so this K here stands for Kosul. Maybe I write K of F, not for K-theory. So that's represented by the complex, which is just F multiplication on A, where you put this maybe in degree 1 and this in degree 0. So this is also just the co-fiber of the map F multiplication by A. And then, I mean, this is clearly a perfect compact object because A is compact itself. So this is compact as A is compact. Okay, so that's a compact object. It also lives in this category because if we invert F, then this map becomes an equivalence. So the co-fiber vanishes. So it lives in D of A on F. And it also generates in the following sense. So if you take any object here, so if M is in D of A on F, an arbitrary object, and we assume that, so if somehow, okay, and this HOM now means the mapping spectrum, or yeah, from this complex K of F to M. If this is 0, then I claim that then it follows that M itself is 0. And then the point is, so this condition here, this is what you have to check for some, that this object K generates the category in the following sense. So you look at the smallest stable infinity category, which a subcategory of this D of A, which contains this object K of F and is closed under retracts. And then, I mean, this you don't even need. You look at the smallest stable infinity category, which contains this object, and then you take the incompletion. And then again, it's completely formal to prove using the adjoint functor theorem that, if you have this condition here, sorry, then this implies that this map from this incompletion to this category in question here, this one, will be an equivalence. So then you have this compact generation. And how do you see this? You just observe that this here, because this is the co-fiber, this you can also write as the fiber of the map F multiplication on M. Okay, but now, so if this is 0, so we see that this implies, let me put it here maybe. So we see this just means that the F multiplication on M is an equivalence. But on the other hand, the condition was that M is in this kernel here. So which means that the localization of M, how do I write this? Let me start here. The localization of M, so this vanishes by assumption on M. But by this condition, this is of course equivalent to M itself. So we see that M is 0. So we have proven this compact generation. Okay. And then this is in fact the base case somehow of the general thing for Zariski localization. So this example is the base case of the following important theorem, which is somehow proved by induction over some Zariski coverings of a scheme. So this goes back to I think Niemann. Okay, let me. Yes.
So you say this is a positive example. Do you mean that if you have the right part of a Bose-field localization, the kernel is not necessarily compactly generated?
Yes.
And in this case, it is.
Yes.
But if you have the left part, it is the right part. Then
yeah. This, if you have if you take the Verdier quotient, then the quotient. I mean, or take the So that's if this D hat is compactly generated and C hat is also compactly generated, then also E hat is compactly generated.
So the problem is when you only know the compact generation of the right part.
Yeah. Then it's yes, right. Okay. So that's the theorem of Niemann, and actually I didn't look up any years, any dates at all. Sorry. So and Bondi. Van den Berg. So this is for classical schemes, and I mean nowadays this has been generalized to arbitrary QCQS spectral algebraic spaces. But let me just state the theorem for classical schemes. So if X is any QCQS scheme, the quasi-compact, quasi-separated, and U in X is quasi-compact open subset, and let's say Z is the complement, then the statement is that all these fibers that appear, so you look now at the derived somehow infinity category of quasi-coherent sheaves on X, which are supported on this closed subset Z. So this is by definition just the kernel of the map from dqc of X to dqc of U, and all these are compactly generated. So this is compactly generated. So this means, so we have dqc, okay, let me just, so this is by definition, I mean, again, it's easy to check that the, okay, let me maybe write this here, dqc of X to dqc of U. Oops, again, it's easy to see that this is always a Bouwsfield localization with the right adjoint is just given by derived push forward. That's always fully faithful. And so we have the sequence, and now this means we can now apply this Thomason-Niemann localization theorem and deduce that we have a Karoubi sequence perf of X on Z. Okay, I just forgot that one should also mention probably. So first of all, let me finish this. This is a Karoubi sequence. And let me also maybe include Thomason here. Because so somehow for the inductive step you need a trick that was introduced by Thomason somehow to prove this. Okay.
The statement is the
yeah, okay.
X on Z is compactly generated.
Yeah, sorry. This was the original statement, and then later on
So in Thomason trouble, I remember, so they proved that, of course, they didn't have the infinity language, but they proved the long exact K theory with negative. So I remember that they had something that worked only for restricted class of schemes, and then it was, I mean, but they proved something like this, that the dqc X on Z is compactly generated, or this is later?
I think it's not formulated in that language. What this refers to is that Thomason had this criterion when a perfect complex on U extends to X, namely if and only if its K0 class extends. And this is what you need for doing the inductive step somehow to prove the compact generation here. This is why I put this name here. I don't think that it's that precisely this form.
No, it was not.
Okay. Okay. It's already 12:35, so I'm supposed to stop here. Then I just maybe indicate now, for example, from this. I mean, this is really the important thing which gives you Nisnevich or Zariski descent. Right? I mean, for example, the easiest case is that you suppose X is covered by U and V, two opens. Then you can compare somehow here perf of X to perf of U and perf of V and the intersection. And then you just see that these kernels, some of these kernels of the localization are equivalent. I mean, they are not the same, but it's easy to see they are equivalent. And then you see both give you fiber sequence of K-theory spectra. And I mean, this term, the corresponding term here is always equivalent. So you see that you get a Meyer-Vittorius sequence for this open covering. And I mean, the same argument works for Nisnevich, and then you can do induction on the number of things in your covering and get Nisnevich or Zariski descent for K-theory. Okay, so that's all for today. So this was somehow I mean, I would like to convince you or remind you that somehow all these descent statements are very easy or formally to obtain. Of course, up to this non-trivial input like compact generation and so on. And then tomorrow I plan to discuss some excision type results where where let's say the situation is a bit different. Okay, thanks.
I'm a bit confused about these. So this last thing you were talking about. So Thomason Thomason have proved that the last sequence is a fiber sequence. There will be
yes. No. No. I think in Thomason.
Can you repeat the question first?
I think the question was what precisely is proven in Thomason Thomason.
Well, it's part of the question, but yes. So my confusion is, if that's what they prove, then you can apply int to this, and I think there will be a map from the incompletion of the sequence to the sequence with DQC, and you will see that DQC will have to be equivalent to int of perfect. So
yeah, I must admit I'm not completely sure what Thomason Thomason proved.
But on the other hand, I think what Waldhausen and Niemann does is the existence of a single compact generator.
Yes, this also, but no, this is not so much more complicated because somehow you have it in the base case of a ring, and then you just need to see that there are finitely many things which together generate, and then you take the direct sum, and then you have your single generator. Yeah, but this is not so hard to see from this inductive proof. I think, if I understand correctly. Yeah, sorry, I don't know precisely. Maybe I should have looked it up. But
of course, Niemann still doesn't use the language. He uses the classical derived categories.
Yes, of course. Yeah.
Yeah, not this. So you have to pass to this.
Yeah. Yes, but I mean, somehow this is not a big difference between the. I mean, if the classical derived category is compactly generated, that's basically the same as for the stable infinity category.
So is it true that the compact generation is determined by the data of triangulation that I triangulate?
I think so. Yes. Yeah. The stable infinity category is compactly generated if and only if its associated homotopy category is compactly generated as a triangulated category.
Sorry, I mean, like, I guess it seems. I mean, I don't really know. I didn't really read the details, but it seems like a little bit of a hard theorem. But nowadays we just don't need it anymore, right? Like to get heuristic descent.
I mean, now you. No, I think. I mean, you still need compact generation or dualizability of these categories. I mean, what you're saying is because of Efimov K-theory, you could forget about this, but you still need this here, and you have to prove this by some inductive argument, and the inductive argument still needs the fiber because you do some induction over the. Yeah.
So you say that a stable infinity category is compactly generated if there are enough compact objects. It doesn't imply that there. What does it imply on the number of compact objects that you need? Is it a small? Is it finite? Is it other cases for example, it's infinite or even not small? I don't know. Not.
Presentable.
I mean,
It's presentable. Maybe it must be.
So
okay. And then you have examples like natural examples where there is no compact generator, but still compactly generated.
with which are compactly generated by not by a finite number, not by one. I mean there are, but yeah.
Like an infinite product of compact.
Okay. So the answer was you just take an infinite product of compactly generated things. I don't know if this is natural enough. I mean, the question was for natural example.
Any more questions about natural?
So is it true that the notion of this post-hook localization is the same as being fiber sequence in PRL-ST, or is there some difference?
No, I think that's the same. So a Bouwspeed localization, how did I call this? Bouwspeed localization sequence is precisely fiber and co-fiber sequence in PRL-ST also.
Okay.
Yeah.
Is it obvious that you have a fiber sequence, you have expected right adjoint? That seems to be obvious.
No, I mean your functor always has a right adjoint because it's in PRL.
Yes, but
and if this is a Bousfield, no. What was the if it's what was the question? If it's sorry, now I'm confused.
Yes, you might require or not that the right adjoint can use it.
What did I say? I think it should follow.
Yeah, I guess if you have a cofibrous sequence, then like the second map should be localization.
Yeah.
Let's thank you again for